Okay, next we have Jaco or Jaco.
Yes, that's right, Jaco.
Jaco is going to talk about towards an optimal global SMEFT fit. So please.
All right. Hi, everyone. I'm Jaco. I'm from Amsterdam, the Nika Theory Group. And some of this talk might have some overlap with the previous talk, but I guess it doesn't hurt to hear some of the SMEFT introduction again, because we have a wide audience with the white. The difference, however, is that I try to implement some of the ideas into a global SMEFT fit, and what exactly a SMEFT global fit is, and in what sense we can reach optimality, I will discuss, of course. First, I'd like to highlight some of the people that I work with. So this is our team. So we have Raquel, Maeve, Juan, Veronica, and myself from Amsterdam, Cambridge, and Milan, and Sussex. So Juliana already nicely explained the idea behind an EFT approach. So just quickly, so for instance, if you cannot detect a heavy resonance, a scalar particle, as for instance in your LHC collider, you might still be sensitive to it in the tail of the distribution. And at low energies, this shows up as an effective interaction between the quarks, in this case, and the top quarks. And simply by including in your standard model Lagrangian all these effective operators, you get sensitive to all possible new physics effect without any explicit assumption about what the new physics might be. So this I try to illustrate by this cartoon. So we have several UV extensions of the SM at low energies. They all reproduce this SMEFT Lagrangian through the introduction of this effective operator approach. So mathematically what this looks like, and we extend it by dimensional operators. At dimension 6, we have, if we don't make almost if you, however, make a couple of additional assumptions about the flavor structure, if you treat all the number reduces significantly to 59. And this cartoon here on the left really is meant to illustrate the fact that the different sectors in this model are connected to each other. So you can have the same operator contributing to different sectors of the standard model, or LHC processes, I should say. So you can have top physics being intertwined with Higgs physics, and you can have all these combinations. And for this exact reason, it's important to include all the coefficients in order to see how they are correlated. This is a bit the same as really casting a really wide fishing net in the ocean that makes you sensitive to all possible tiny correlations. And only this way you are able to pick up the bigger pattern, if you wish. So what are the properties of the SMEFT? So it's a systematic parameterization of the theory space close to the SM. It's a low energy limit. The complete theories in the sense of the cartoon that I showed. Yes, please. The previous slide, yes. Yes, so if you are completely generic, you do not make any assumptions about how the different flavors might interact. Of course, you can have flavor changing neutral currents if you are completely generic, which is not allowed in the SM. Does that answer the question? Okay. Right, so the operators here, and in red is the dimension 6 one, depend on the SM fields, and you can form a complete basis at any given mass dimension. This means that if you write an operator randomly at dimension 6, I can reduce it through the equations of motion, integrating by parts, to a subset that forms my basis at dimension 6, 7, and 8. And this has been done, and there's a huge list, and this is the Warsaw basis. It's fully renormalizable order by order in this lambda expansion. I think Galileo didn't like what I said, or okay, and it can be matched to any BSM model that you later on design right? So if you want to introduce an explicit new particle, you can connect it to the SMEFT approach later on. So just a quick example. So it would be a chromomagnetic dipole operator at dimension 6. So you have two quark fields, Q and T, and a Higgs field and a field answer. This is, if you do the counting right, dimension 6. And if you look at the possible interactions that you can get, for instance, if you combine the two gluons from the field strength tensor with the two quarks, you can get this 4-point interaction. If you take only one gluon, you get this 3-point vertex, right? So this introduces modifications to the SM. The Lagrange changes, and because of that, the cross-section also changes. And you get two contributions. The linear term between the SM and the EFT. And then if you take the pure EFT correction, you get a squared contribution, which is this last one. So fully generically, if of them, you can write it this way. So this term is the only term that includes operators of dimension 6 without dimension 8. This lambda 4 correction in principle includes interference terms between dimension 8 suppressed by lambda 4 and the SM, but we choose, or many people, many groups choose not to include these for now. So we stop at dimension 6. So now the name of the game, what is a SMEFT? Whatever that means. So you compute these cross-sectional channels, you compare to data. So you have your SMEFT cross-section parameterized in terms of the Wilson functions, these Cs. And then you construct your chi-squared and you compare to experimental data and you include the covariance matrix and you just minimize it. It's a multi-Gaussian log likelihood optimization problem. And many groups perform this analysis, including we. So there's the SMEFT tool that includes 317 cross-sections and there are 50 EFT parameters here on the horizontal axis, and you can read off the constraints. And so far there has not really been any significant difference with the SM. The problem, however, with all of these tools is that they take LHC cross-sections that are not really designed for an EFT analysis a priori. They were already out there and we are just taking them for our analysis, and it's not necessarily optimal. We can maybe gain sensitivity in the exact same sense as Juliana just nicely explained. Right, so the question is, can one do better? Just starting really simple. So what changes if we go from bin to unbinned? So you write down your likelihood. You have a couple of bins, and you can ask the question, what is the optimal number of bins, right? Does it change if I insert more? And if I measure the cross-section differentially in additional kinematics, do I get an extra sensitivity in my analysis? So these are the two questions that we try to answer. And I should note, of course, that if your bin has less than or fewer than 30 events approximately, you should not use the Gaussian, but the Poissonian likelihood instead. So the main goal in this project is to construct these unbinned variables and assess their relevance for SMEFT global fits, impact compared to the traditional approaches that I just explained. So we write this extended likelihood or the extended likelihood. So it's an overall term that is sensitive to applying a kind of likelihood term that is sensitive to the shape of the distribution. And this F is simply the probability to observe an event X. It's a feature factor in machine learning lab at your as an event normalized to the inclusive cross section. And by construction, I should mention that this is the most optimal that you can get, right? You cannot gain any extra sensitivity if you include all the features from the start. So the EFT approach, so far I've not really specified anything specific to the EFT approach, but EFT has this nice that it can be written as a polynomial in the Wilson coefficients. And for the purpose of limit setting, you only need to have a ratio with respect to some reference. And so you take this likelihood ratio with respect to the SM, and you get this linear term and the terms. And by comparing it to the likelihood that you already have from a SMEFT global analysis, you can assess the sensitivity that you gain by including these unbinned observables. Right. So just like before, to approximate these coefficient functions R in front of the C's by neural nets, and this should scale well to an arbitrary number of EFT coefficients, because I mean, we have, if we don't have any assumptions, 2,500 operators, right? So the method better scales well with the number of coefficients. And we want to include a measure of the uncertainty of the analysis. And I think this will be discussed on the next slide, actually. First, how do we obtain this likelihood ratio? So Juliana used the quadratic loss. You can use the cross entropy loss as well. So if you minimize this function with respect to this loss function with respect to G, you get an object that is 1-to-1 with the likelihood ratio that you need for inference, right? And this has two terms. So it's a term sensitive to EFT physics and a term that is sensitive to SM physics. So by generating Monte Carlo events under both hypotheses, you obtain samples in the EFT SM. So imagine generating EFT events at some fixed coefficients Cj that you can set to 10. Yeah, your ratio at the linear level at least takes the following form. And then this machinery of minimizing the loss, you're bound to get convergence if your network is sufficiently flexible to the object that accompanies the linear term in the EFT cross-section ratio. Then you can, of course, do the same game at the quadratic level. So you just generate EFT events with only two coefficients turned on. And in this case, all the linear terms cancel, and you're only left with this last term. So this way you can systematically obtain all the R functions, all these guys for any J and K. You can obtain this simultaneously in parallel at the same time. It takes as much time to obtain one as it obtains to take 2,500, right? How does the training look like? So I'll show you an animation in 1D of the object G that enters the loss function. So remember that L is a function of G. So if I perform the training and wait long enough, at some point, the neural net should approximate the truth result, which I show here in red. And you also see a couple of lines here. So what are these lines? These are replicas. So we want to assess the neural net uncertainty. And we do this by generating a couple of events at different seeds and training a neural net on each of these. So we have a set of 50 data sets under the SM and the EFT, and we just redo the training 50 times. And those are the lines that you see. And this allows us to propagate the model uncertainties to the space of EFT parameters, very much like the NMPDF approach in PDF fits. Right, and this was explained by Alessandro on Tuesday. So if you want to know more, you can check this talk. So the same animation, but now in 2 dimensions. So this is for, by the way, this is for top quark pair production with 2 features, the invariant mass here and the rapidity. If you just let the training run, you converge to the truth result. And here the ratio between the 2, and you're getting closer and closer to 1 as you let the training evolve. Because we have included multiple replicas, we can assess the uncertainty and plot things like the pool, how statistically analysis throughout phase space, and you get good agreement. So the pool is within 1 sigma more or less everywhere. Right, so cross-section positivities. In the previous talk, the cross-section was written as a quadratic polynomial from the start, so it was bound to be positive. But now, because we are splitting up the training to make it parallel, the cross-section can, during training, become negative, and then procedure just crashes. Just the lock is not defined anymore of the loss function. So we need to do something here. So either you penalize such through a Lagrangian multiplier that it can only obtain or get positive ratios R, or you just rescale your neural network outcome such that EFT coefficients gives you something positive. This is a bit technical, but this is what we take care of. And the number of processors really scales like order n, so making our approach suitable for large EFT parameter space. So onto the results. So first we took a toy model, top quark pair production, bint in the invariant mass of the top quark pair. On the left, I'm comparing for two EFT coefficients, how the bounds or the exclusion limits change depending on the binning. Of course, if you're completely inclusive in only one bin, you get nothing, right? You just get a circle. If you start adding more and more bins, on the right, for instance, you get closer and closer to the here you keep the completely unbinned likelihood. The machine learning model in green, without having access to this likelihood ratio, it just has access to the events, does obtain similar performances, right? So this is good news. So this is the way of validating our results, which we've done, by the way, using form calc. It's a really nice tool in which you can insert a UFO model and you get the analytical cross-section as a function of the Wilson coefficients. It's not really important, but for the people that are interested, what I did, this is how you can obtain analytical predictions in the SMEFT. So a bit more realistically, we then moved on to Higgs-associated production and top quark pair production, and now I'm only going to show you a view of time results for ZH with the decays to L plus L minus and the BB bar pair with the following set of operators. And we make sure to use the same operator basis as the SMEFT global analysis to be able to integrate them later on. So the first step would be to just run MATGraph and obtain these distributions and see what they look like. And then rescaling them to a region between 0 and 1, or between -1 and 1, you need to bring them all on the same scale in order to have your neural network not pick up or be sensitive to one particular feature. They need to be brought all on the same scale. So this we take care of. And then this is what we get, right? So this is just a tiny selection of the operators that we did. So this is a corner plot of SMEFT marginalized over the operators. I'm comparing a binned approach PT of the Z boson with the machine learning model trained on only PT of the Z boson. And of course, I mean, maybe not of course, but you do see that you get a significant improvement in terms of sensitivity. So in blue, the contours in blue are much better than the ones in orange. So this shows that this particular SDXS binning is suboptimal for EFT studies. And it also provides one with a useful benchmark, right? Because you cannot do any better than this if you decide only bin in PT. The contours in blue, I mean, are the most optimal that you can possibly get. So by choosing binning, you can, by comparing it to the blue contours, know how far away you are from optimality. And because now we have excluded systematic uncertainties, we need to make sure that the statistical uncertainties dominate. So we put a lower bound on those to ensure that we're not just neglecting systematics, but they can rightfully be neglected compared to systematics. So including the other features in green, in some cases it doesn't really lead to much improvement, right? And this is fine. I mean, it just tells you that binning in PTZ is sufficient. In some cases, however, you do get some improvement. So here is the same overview plot, but with 7 features in these 3 cases, for instance, you do see an improvement. So in this case, it would pay off to include these additional features. And analytically computing a differential cross-section in all these 7 kinematic variables is just impossible, right? So this is really the upshot of this approach. So just to wrap up and conclude, so the SMEFT provides model-independent framework to search for new physics that fully takes into account correlations between different sectors and connects BSM models. And a global SMEFT fit will profit from including unbinned observables. And we are planning on extending the SMEFT fit code with these unbinned observables in a couple of weeks. And our approach, I should stress this, our approach really scales well with the number of coefficients, care of the uncertainties, the model uncertainties through the replica method. And the last point that I showed was that we can use this tool as a useful benchmark to compare against the most optimal bounds that one can possibly get. Okay, so with this, I'd like to conclude and thank you for listening, and thank you very much.
Okay, Jaco finished with a lot of time left on the clock, so we can have plenty of time for discussions. Yes?
I didn't quite understand. You've got 50 parameters altogether in your fits. So you were showing sort of like two-dimensional plots of the parameters. So what's happening to the other 48 parameters on those? Are they kept at 0, or are they allowed to vary, or are they completely irrelevant?
Right. So it's really the coefficient functions in front of those C's that you refer to that we use to obtain these plots. So these ellipses have been obtained by taking all of these 50 replicas and taking the median. And then we take this median to obtain these limits. You can also show the pool in which you really take this uncertainty into account to show but for the analysis further down the chain.
Yeah, the question was.
I don't know.
59.
Yes.
Did you set all of those to 0?
Oh right. Oh no. Right. So we turn them all on. So it's a global fit with. In this case, sorry, I misunderstood your question, I think. Yeah, so in this case, in this corner plot, so this would just subset, right? We would just allow all the full coefficients to vary. And then we marginalize over the ones that I don't show here.
Okay.
Right? Does it answer the question?
Yeah.
Okay.
Any other questions? I have a couple of questions. So how come in some of the examples you showed, it looked like the ML model error bars were a bit larger than the bin, like in the next slide maybe? Or the slide after that? Yeah, is it just an artifact of the interpolation or something? It looks like
this is a numerical artifact.
Yeah.
Yes. Yeah.
Basically they're the same.
They are the same, yes, but we cannot tell them apart numerically. Yeah. So it might be, I don't know how to, we have different replicas behind this, and I'm only showing the median. But if you are able to find some way of using also the other replicas, then you might be able to put a measure on this difference.
Also, I was wondering, when people actually, these are toy studies where you didn't take into account like detector effects or anything.
True.
So when people actually do SMEFT fits, how are they doing them? Are they unfolding the data to to the parton frame or something? I see. And does that introduce additional uncertainties and things which are realistic?
Yes, a lot. And these are reported in the CMS and ATLAS papers as much as they can. And these we just take as input, to the fit. We just put this into the covariance matrix.
I guess my question would be, are the uncertainty bands you're showing here just at the parton level, how do they compare to the uncertainties you get from the unfolding? If the unfolding introduces much bigger uncertainties, then are you actually gaining anything here, or it's a subdominant uncertainty compared to the?
I think you're losing sensitivity by doing this unfolding. So
yeah.
But I don't have access to these
Yeah.
It's not a dominant.
No, it's not, okay.
I see.
Sorry, I cannot hear you.
From the last week talk, this is before hadronization, no?
Yes, this is at the particle level, in fact.
It's not even unfolding, which you have to take into account because it's you don't see the it's before PTIA, let's say. Yeah, I was thinking of the detector only unfolding, yeah. But if particle level, you have to be able to reconstruct the neutrino, no, in this unfolding.